So to topologically sort a DAG, the first algorithm that we come up with relies on DFS itself. So the topological sort algorithm based on DFS relies on the following observation. So suppose there is an edge from U to V. Then we claim that it must be that the exit number of V is actually smaller than the exit number of U. There are two cases to consider to justify this claim. So the first is that when DFS of U explores its neighbors and it looks at the edge UV, V at this point is not marked. So at this point we have DFS of U which is currently operating, and it invokes DFS of V recursively as a part of the DFS procedure. So clearly DFS of V must exit before DFS of U exits. So in this case it's pretty clear that V comes off the stack first, so its exit number is strictly smaller than the exit number of U. So the other possibility is that V was already marked when DFS of U found the edge UV. Well, in this case, it is clear that we must have already finished DFS of V because it's marked. And so since DFS of V is already finished, so why is it finished? Because there was some other edge of the form W to V, right? So we are looking, so we have already gone through some edge W to V, and then now we come back and through DFS we come to U, and now when U encounters V, it's already marked. So in this case, DFS of V was already finished, so its exit number has already been computed. So DFS of U will have a strictly larger exit number. So in either case, whenever there is a dependency, then the dependency from U to V will imply that the exit number of V will be smaller than the exit number of U. So this immediately gives us the following DFS based algorithm for topological sort. So we run DFS of G and compute the exit numbers of all the vertices. Now as a part of DFS, if we actually discover a back edge, this means the graph is not a DAG. So in such a case, we should report an error in exit. But assuming that we don't find any back edges, we have now computed the exit numbers, and now with our observation that whenever U points to V, the exit number of V is smaller than the exit number of U, then it suffices to print out all the vertices in the decreasing order of exit number. So we just have to list the vertices in their decreasing order of the exit number. So let's see how this DFS based algorithm works on the example with the courses that we had before. So let's start our DFS, for instance, at C1. Okay, so this now has entry number 1. Now from C1 we explore C3, right? So this has entry number 2. From C3 we would explore C4. This has entry number 3. And then from C4 we explore C5, and this has entry number 4. And now we find that we cannot explore anything from 5, so we exit from 5. So exit from 5 means C5 has entry number 1, exit number 1. Going backwards, now 4 has no more edges to process, so this has exit number 2. 3 has no more edges to process, so this has exit number 3. And finally 1 has no more outgoing edges, so this has exit number 4. And since we haven't marked C2 as yet, we will now process C2. So we enter C2 fifth, and we also exit C2 fifth because we can't process anything anymore. So in this DFS we have computed the entry numbers and the exit numbers. Now if we enumerate this in the reverse order of the exit number, so C2 has the highest exit number, that is 5. Then the next one is C1, which is 4. Then we have C3, which is 3, C4, which is 2, and C5, which is 1. And this we can see is a valid topological sort because C2 and C1 can occur in any order, they don't have any prerequisites. C3 requires both of these, so it appears after them. C4 requires C3 and it appears after that. And C5 requires both C3 and C4, so it appears after both of them. So what is the worst case complexity for this DFS based algorithm for topological sort? So clearly there are two phases in the algorithm. We have to do a DFS and we have to sort the edges in reverse order of their exit numbers based on the DFS. So we've already seen that the complexity of DFS depends on the representation of the graph that we use. So if we use an adjacency matrix, then DFS takes order n squared time. On the other hand, if we use an adjacency list, it takes time order n plus m, and so this is better if we have small number of edges. Now sorting the vertices in reverse order would take time order n log n. This would not affect the complexity of the adjacency matrix based algorithm because that takes time O n squared anyway. On the other hand, with the adjacency list, if we took time O n log n to sort, we would actually be reducing or worsening the complexity from n plus m to n log n plus m. But fortunately, we don't actually have to sort. What we do is we just list the vertices as they are generated. Right? So as they come off the stack, we list them, and so they are now in increasing order of exit number. But we want them in decreasing order of exit number, so we just reverse this list. Right? So we don't need to explicitly sort, we just need to reverse the list of vertices after generating them in increasing order of exit number. So alternatively, we can come up with an algorithm which directly uses the decrease and conquer strategy. So let us say that a vertex is a source vertex if it has no incoming edges. So the claim is that every DAG has a source vertex. So supposing a DAG does not have a source vertex. So we start at any vertex, okay, say V1, and then it's not a source vertex, so we can go back and produce another vertex V2 which points into it. Now again, this is not a source vertex by assumption, so we can go backwards and produce a vertex V3 which points into it. So we can keep doing this because none of these are source vertices, and eventually we would have to produce a vertex Vn which points into Vn minus 1. Now if there are only n vertices and this is not a source vertex, then it must also have an incoming edge. But now its incoming edge must be from one of the vertices we have seen before, because there are only n vertices altogether. So if none of these are source vertices, then we have a cycle, and therefore this is not a DAG. Right? So if every vertex is not a source vertex, then the directed graph cannot be a DAG, and therefore every DAG must have at least one source vertex. So with this observation, we can see, of course, that a source vertex can be enumerated first in a topological sort, because a source vertex has no incoming edges, so no dependencies. Now, having enumerated a source vertex, supposing we remove it from the DAG. Now, obviously, by removing a vertex, we are not introducing any cycles. So if you remove a source vertex from a DAG, what we have is still a DAG. In other words, we can then recursively process the rest of the DAG and produce a topological sort for the remaining DAG, and the remaining DAG will produce a sequence which can be appended to this source vertex to give an overall topological sort. So this yields the following decrease and conquer algorithm for topological sort. So we start with a non-empty graph. We identify a source vertex, append it to the topologically sorted list, and remove this vertex from the graph. So since we are removing vertices from the graph as we go along, we keep repeating this so long as the graph is not empty. Eventually we will enumerate the last vertex in the graph, and then we will have a topological list of the entire graph. The decrease and conquer topological sort works for our example with the 5 courses. So what we will do to determine which are the source vertices is to compute what is called the in degree of V. So in degree of V is the number of incoming edges to every vertex V. So initially from the given graph, we have in degree of C0, C1 is 0, C2 is 0 because there are no incoming edges. The in degree of C3 is 2, the in degree of C4 is 1, and the in degree of C5 is 2. So a source vertex is one which has in degree 0. So what we do according to the algorithm is identify a source vertex and enumerate it. So in this case, let's pick the smaller of the two. So we pick C1 and we enumerate it. And the second step is to remove it from the graph. So now we remove this graph, we remove C1 from the graph, so we also remove this edge. And the result of this is we have a new graph with 4 vertices, but we have to recompute the in degrees. Right? So if we recompute the in degrees, it turns out that now the in degree of C3 has become 1. So at this point, we again look for source vertices. We still have a DAG with 4 vertices now. And in this case, the only source vertex is C2. So we enumerate C2 and go through the same process. We remove C2, remove this edge, compute in degrees again. So these in degrees don't change because nothing pointing into it has been removed. But C3 does reduce, and now C3 becomes a source vertex. So in the next step, we can now enumerate C3 because after 2 deletions, its in degree has become 0. So now we remove C3 and we remove these 2 edges and recompute the in degrees. So this in degree becomes 0 and this in degree becomes 1. So at this point, C5 is not a source, but C4 is. So we can do C4. Okay. So having done C4, then we again delete C4, recompute the in degrees. So there's only one vertex left, so it has no edges. and therefore we now compute C5 and we are done. Now if you remember the DFS based sort, we actually computed C2, C1, C3, C4, C5. As we remarked in the beginning, the topological sort ordering is not unique. In this case, because C1 and C2 are both source vertices, there is no fixed order in which we must do either of them. And so we can have multiple topological sort orderings for the same DAG. So here is a more detailed exposition of the algorithm for topological sort based on decrease and conquer. So what we have to do is to systematically keep track of source vertices and keep removing them from the graph. So for this, as we said before, what we need to do is compute the in degree of every vertex. So initially, we note that the in degree of every vertex is actually 0. And then what we do for every edge in the graph is to increment the in degree of the target of the edge. So if VW is an edge, then we increment the in degree by 1. So at the end of this, processing all the edges in the graph, we have correctly computed the in degree of every vertex in the original graph. Now we have to identify the source vertices. So these are source vertices whose in degree still remains 0 in spite of processing all the edges. So for every such vertex, what we do is we remember it in a queue. So we keep a queue of all the current source vertices. And now we process this queue. Right? So we pick up the head of the queue and enumerate it. So currently V is in the queue, it's a source vertex. We enumerate it, delete it. So we never look at it again. But when we delete it, we also have to update the graph. This graph no longer has V, so for every edge VW, we have to discard this edge and decrease the in degree of W. Right? So for every edge pointing out of V, we decrease the in degree of the target, and if in the process this particular target happens to become a new source vertex in the reduced graph, then we append it to the queue. So in this way we keep putting, as we encounter new source vertices in the process of deleting vertices from the graph, we keep adding them to the queue, and eventually all the vertices will get into the queue and come out of the queue, and when the queue is empty, we have finally got a topological sort of the entire graph. So the complexity of this algorithm depends on the representation. Right? So if we are using an adjacency matrix, right? So let's go through each step and see how long it takes. So to initialize the in degrees to be 0, whether you're using a matrix or a list, is going to take O(n) time. Now if we want to examine every VW in E in an adjacency matrix, we have to go through every row in the matrix, and so this is going to take us order n squared time, because we have to go through the entire adjacency matrix row by row. And now again we go back through all the vertices and we spend again order n time in order to update the set of source vertices. Now we come to this loop. So clearly the outer loop is going to happen once for every vertex. So this is going to happen O(n) times. And now in an adjacency matrix representation, whenever we remove a vertex, we have to scan all the outgoing edges. So this is again going to be order n time, because we have to look at the entire row for V in the adjacency matrix. So this entire thing becomes again O(n) squared. So we have O(n), O(n) squared, O(n), O(n) squared. So for the adjacency matrix representation, the overall complexity is O(n) squared. On the other hand, if we use an adjacency list representation, so this first initialization of all the in degrees to 0 is still O(n). Now when we scan through all the lists, we will examine each edge exactly once. Right? So this process of updating the in degrees will take O(m) time. Now we go back and we identify the source vertices. So this again takes O(n) time. And now the outer loop here is going to be O(n) again, because we have to process every vertex once in the queue. But at this point, this is going to take degree of V time, because for every V, we only have to look at the list for V. So exactly as many outgoing, so this is out degree technically. Right? As many outgoing edges as there are from V, we have to look at that, but that will be given to us directly in the list for V. And overall, across all the vertices, this inner loop takes again O(m) time. Right? So what we end up with seeing is that in this representation, if you use adjacency lists, then actually this algorithm takes O(n) plus m time. So let us summarize the complexity of the two algorithms that we have seen. We have a DFS-based algorithm and a decrease and conquer algorithm, and we have two different representations, adjacency matrix and adjacency list. So what we have seen is that for both of them, we would need time O(n) squared if we use an adjacency matrix representation. On the other hand, if we use an adjacency list representation in the DFS-based algorithm, by reducing the sorting problem to reversing a list, we can keep it at time O(n plus m, which is the same as for DFS. And for decrease and conquer, again, by keeping a queue, we can keep the time down to O(n plus m. So in both cases, for adjacency lists, we get a better complexity, especially if the number of edges is small. So to summarize, so topological sort is an extremely important practical algorithm because very often we have to work out a practical schedule for tasks which have dependencies. So topological sort is an efficient way to organize these tasks into a DAG and then list them out in an order which is feasible. So we have seen two important algorithms for this, one using DFS exit numbers and the other one using a decrease and conquer strategy.